Hey there, I'm Justin Scott, your Transit TV Science Genie. Have you ever noticed how some insects effortlessly glide across water without sinking? Or how a carefully placed paperclip will float on the surface? They're both related to the same phenomenon, surface tension. So if you remember back to our examination of hydrophilicity, you know that water molecules have a strong tendency to self-associate with one another through hydrogen bonding networks. Well, a consequence of this is that for water molecules positioned at the air-liquid interface, they have a stronger pull to interact with the other water molecules inside the drop than with the surrounding air molecules. This creates what is known as surface tension. Now, what is extra cool about surface tension is how it can be visualized through what is known as the magic milk experiment. While milk is undoubtedly a more complex mixture than water, it still experiences the same forces as described above, which yield surface tension. To begin, take a plate and cover the bottom of the dish with milk. Now, add some drops of food coloring to the surface. Let's use some different colors and spread them out a bit across the plate. Notice that while the drop spreads out a small amount, it mostly stays in place. To release the surface tension responsible for keeping the dyes in place, simply add a touch of dish soap. And look at that! Just like that, all of the colors spread out across the surface. So what's happening? Believe it or not, it's actually not magic, but pure science. Again, calling on the concepts of water-loving, water-fearing molecules, we find that the primary agents in soap belong to a class of molecules known as surfactants, which have the quality of being amphipathic, simultaneously water-loving and water-fearing at the same time. You may ask how this is possible. To see what's going on, all we need to do is examine the molecule. For most common dish soaps, the active ingredient is usually sodium dodecyl sulfate, or SDS. You can see that the molecule contains a negatively charged head group, a sulfate moiety, which allows for favorable interaction with polar water molecules, while the long hydrocarbon tail is hydrophobic. The sulfate groups position themselves at the surface, allowing those previously restrained water molecules to freely and favorably interact with the sulfate groups as well as other water molecules, while the hydrocarbon tails now provide the interface with air, an interaction which does not produce the same surface tension as before. You can see that after enough addition of soap, the surface tension is effectively entirely dissipated and the color stops spreading as the surface approaches being completely covered in detergent. So while it may have seemed like magic at first, a closer look at the system reveals the beautiful underpinnings which are fully explained through fundamental science. That's it for us. I'm Justin Scott, your Transit TV Science Genie, reminding you to always ask questions.